So ionization energy is defined as the energy required to strip an electron from the atom. Now, there is a ionization energy to strip off one electron. There is an ionization energy to strip off the second electron. That's called IE2. A third electron would be IE3, so on and so forth. Now, this is an energy, so energy or quanta is being applied to the element to get it so that it becomes ionized, that you rip off or tear an electron out of the atom. It becomes liberated. The definition is a little bit more technical. If you look at the textbook, the ionization energy is the energy required to remove 1 mole of an electron from the gaseous state. So with that technicality that you're looking at it from 1 mole of the element and in the gas state, with that technicality, we will just summarize it for simplicity's sake as the ionization energy is the energy required to strip an electron from an atom. The trend of the ionization energy, we'll talk about the first ionization energy here, is that it's going to increase from left to right in the periodic table, i.e. 1. Okay, that's the energy required to remove 1 electron. So the trend is that it increases across a period, left to right, and it also increases down a group, left to right. So that would be IE1. Now, IE1, the ionization energy to strip off 1 electron, is going to be less than IE2, okay, which in turn is going to be less energy required to strip off a third electron, and then less energy required to strip off a 4th electron. In other words, to strip off the 4th electron will require more energy input than it is to strip off the 3rd electron, than it is to strip off the 2nd electron, than it is to strip off the 1st electron, so on and so forth. The reasoning behind this is pretty simple, because as you remove electron and electron and electron, you see it's very easy to remove the outer electrons, the valence electrons, but it's very hard once you get to the core electrons, those that are very housed near to the nucleus. It becomes larger and larger and larger energy input required to get and strip off the core electrons. But stripping the valence electrons, no problem. That's why over here in the periodic table, the ionization energy is very low. Remember, these like to be +1, +2. Take the electron so I can achieve noble gas status. Take my +2 electrons if I'm group 2A so that I can achieve noble gas status. Now over here, in contrast, it's a very different story. Okay, these guys, particularly halogens, very much so the halogens, oxygen, nitrogen, phosphorus, these guys will gain electrons to become noble gas status in terms of their electron configuration. So we would imagine these electrons, particularly those that are housed in the p block, this is the p block of the periodic table, those are going to take a lot of energy. It's going to require a lot of input to get those electrons out. Quite the contrary, they want those electrons in. Taking an electron out messes up with its stability. So that's why we have this trend, but there's a lot of deviations from the trend. So in this next situation, we want to show you a little bit of differences. Particularly the differences I want you to recognize are between when you look at group 2A of the periodic table versus group 3A, and then also bucking the trend or a deviation from the trend is the 5A elements tend to have a greater ionization energy than the 6A elements. So let's take a look at that very closely here. As an example, let's look at the electron configuration of aluminum versus the electron configuration of magnesium. So look at where aluminum is housed in the periodic table. Okay, aluminum is housed in group 3A and magnesium is housed in group 2A. So the 2A and the 3A tend to disavow or tend to not follow the trend. In order to do that, let's fill in the electrons. It's very important as a common theme here that you know electrons are going to march in a very specific order in a very specific set of orbitals. So let's write them out. Okay, let's first do aluminum first. Aluminum has 13 electrons, so we're going to fill out the electrons for aluminum and its 13 electrons. So 13 electrons of aluminum. Here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so those are the 13 electrons of aluminum. Remember ionization energy, the energy required to remove an electron. Okay, let's look at magnesium here. Magnesium is 12 electrons. So, okay, the same scenario, 12 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So here's our 12 electrons here. So ionization energy is the energy required to remove an electron. And what I'd like to convince you is the ionization energy is less here. So removing an electron there, sort of erasing it, takes less energy. It takes less energy because when you remove that electron, you have a full 3s orbital. It's much more stable. So the situation is much stable when you remove an electron from aluminum. Now consider removing an electron from magnesium. All right, so removing an electron from magnesium, making it Mg+. This does not look very stable because you have that lone pair of electron that's not paired up. And you have some spin up that's with a 3s orbital. Spin up and spin down is a lot more stable, and it's going to take a lot more energy. This is not very much energetically favored to remove an electron. Actually, this is more happy and content like this. Okay, removing an electron here. Okay, let's erase this. Gives you this situation. It actually gives you the same electron configuration of magnesium. That's pretty stable. All right, so. Again, this kind of bucks the trend. We would expect, based on our trend, that aluminum would have a greater ionization energy than magnesium. Actually, it's a violation of one of our trends. Aluminum has a much smaller ionization energy than magnesium. Once again, because removing that electron from aluminum gives you a full 3s orbital, no high energy electron. Remember, as you add electrons, you're going higher and higher and higher in energy. So removing an electron here makes everything full. Okay, there's nothing half paired. Removing an electron here in magnesium is kind of difficult. Okay, it's kind of a pain energetically wise. It can take a lot of energy because everything's already full, everything's already paired. So that is one example of a deviation in the trend. You can also look at another deviation of the trend if you look at 5a and 6a. So that's going to be between nitrogen and oxygen. So nitrogen, I'm just going to look at the 2p orbital here. So the 2p orbital of nitrogen, let's just look at the 2p orbital of nitrogen. So it's going to be 2s2, 2p1, 2p2, 2p3. All right, and looking at the 2p orbital electron filling of oxygen, it's going to be, so we got 2s2, 2p1, 2p2, 2p3, 2p4. So 2p1, 2p2, 2p3, 2p4. It's going to take less energy to remove an electron. It's going to take less energy to remove an electron from oxygen energy than it is for nitrogen. Again, this is a deviation from the trend because if you remove an electron here, I'm going to blotch out this electron, you get a half-filled 2p orbital. That's not bad. That's pretty good. Nitrogen, it's all half-filled. This is a very stable situation. Now, if I remove an electron here, that's going to take a lot of energy to remove an electron, blotching it out or removing it, because what you have left is something that is just two unpaired electrons. And that's energetically a little bit unstable. Having a full 2p electron that's completely half-filled, having a 2p electron that's completely half-filled is much more stable. So again, a violation of our general trend in ionization energy. It takes less energy to remove this electron, because now you have everything unpaired and half-filled, than it is to remove this electron in nitrogen, because now you have two unpaired and then one empty slot. This is generally, energetically speaking, not good, versus this, which is energetically favorable.